approximate algorithm used to solve the graph coloring problem. So graph coloring problem refers to the problem of coloring vertices of a graph in such a way that no two adjacent vertices have the same color. This is also called vertex coloring. So in a graph, no two adjacent vertices should have the same color. So that is meant by the, for example, consider this graph. These are two adjacent vertices. They should not have the same color. If this is C1 is color 1, then this first node is having color red, then the other nodes, the adjacent nodes should not have the red color, means the same color they should not have. In the smallest number of colors required for coloring a graph is called the chromatic number. Smallest number of colors required for coloring the graph. Coloring is done using at most, satisfying this condition, if coloring can be done using at most k colors, it is known as k coloring. The chromatic number is denoted by this letter x of g, chromatic number of a graph. Finding the chromatic number of the graph, that is minimum number of colors required to color a graph so that the adjacent vertices should not have the same color. So that is the graph coloring problem, which is an NP complete problem, which means it will take exponential time. It has both decision version and optimization version. Graph coloring problem, the decision version is a yes or no question, that is with a given m colors and graph G, whether such color scheme is possible or not. For example, a graph is three colorable or not. The optimization problem states that given m colors and graph G, find the minimum number of colors required for graph coloring. It has several applications, for example, design timetable, Sudoku, register allocation, the compiler, map coloring, etc. The input to the graph, we already know that it is an adjacency matrix. So here a graph is given here, and the input to the graph is given as the adjacency matrix. Input of the input, which means the graph is represented as an adjacency matrix. So here this C1, C4. If there is an edge, it is marked as 1. C1 to C2 there is an edge, so it is marked as 1. C1 to C4 there is an edge, that is marked as 1. Wherever there is edges present, that is marked as 1 in the adjacency matrix. The problem can be solved by, so in this problem the condition or the requirement or the constraint is no two adjacent vertices have the same color. So here if we use, there are 5 nodes in this graph, so if we use 5 colors, then each node is having different color. So no two adjacent node has same color, but it is not an optimal solution. We have to find the minimum number of colors. But here see this graph. In this, using only 2 colors, this graph is colored without the adjacent vertices having the same color. So this is the optimal solution for this one, and which uses only 2 colors. So this graph coloring problem, which can be solved using different approaches. One approach is greedy technique, another approach is backtracking method. To find the exact solution for the graph coloring problem, we can use backtracking algorithm. But this will take exponential time. That is why we are going for the approximate algorithms. So before that, we can just see how this graph coloring problem is solved using backtracking. So algorithm backtracks whenever color I is not possible to assign to any vertex k, and it selects the next color I plus 1, and test is repeated. So consider this graph A, B and C, D. How to color this graph and what is the minimum number of colors we can. So using backtracking, we can draw the state space tree. So this is first the nodes are represented on the left side like A, B, C, D, A, B, C, D, and the colors are represented as 1, 2, 3. So this is the graph, the corresponding state space tree A, B and C, D. The edges are A to B, B to D, D to C and C to A. So we draw the graph here so that it can become can be compared with the state space tree. So this is node A, and from here to here this is node B, this is node C, and this one is node D. And these are the edges of the graph. So node A, first color 1, it is given to node A. So this means node A is given color 1. Then node B will in the state space tree, first option we will see whether it can be given color 1. Node A has given color 1. So node B cannot be given color 1 because node B is adjacent to node A in the graph. So the algorithm, this one backtracks, showing using the dotted lines, backtracks. And then it goes to takes the next color 2, and assigns the color 2 to node B. So here node B is getting color 2. Then it goes for the next node C. Node C. Node C, first it will try for assigning color 1. Checking for color 1, node C cannot be given color 1 because it is adjacent to, node C is adjacent to A. So the algorithm backtracks and tries to give color 2 to node C. So node C color 2 is possible because it is not adjacent to node B. So node C is given color 2. Then node D, we can consider color 1 first we will consider. If color 1 is not possible, then only color 2. Color 2 is not possible, then only color 3. So now for node D, we will try for color D. So now node D will try for color 1. It is possible. So does not backtrack and we'll assign that color. The other options are also shown here. What are the other possible options are shown? So the answer is it is two colorable because we have only used two colors for coloring this layer. So this is the backtracking method. Complexity analysis for this method is given here. That is the number of a node decreases exponentially at every level in the state space tree. The state space tree, every level, the number of nodes is exponential increase. So the graph coloring algorithm runs in exponential time, which means it is an NP complete problem. So that is why we are going for an approximate solution, an approximate algorithm which gives a solution in lesser time. And we can see another example of the graph coloring problem. Apply backtrack on the following instance of a graph coloring problem of 4 nodes and 3 colors. See, this is a given graph, and we can see the 1, 2, 3, 4. We can see, so here we have not drawn the complete state space tree, we have shown the solution tree only. Solution options only we have shown. So the graph which has to be checked whether it is, which has to be checked for the minimum number of colors is this one. 1, 2, here it is 4, here it is 3. And these are the connections or edges. So now we can start from the vertex 1. So vertex 1, first we are assigning color 1. C1 we are assigning for vertex 1. Then now we can see for vertex 2. Vertex 2 is just going for vertex 2 and try to assign color C1 to vertex 2, but it's not possible because it is adjacent to vertex 1. So the algorithm backtracks here, and then it will try for another color 2. Color 2 checks whether it is possible, to assign color 2. It is possible. So it is assigned color 2. Now it will check for the other vertex 3. Vertex 3 try to assign color. Every time it will try in the order, that is C1, C2, C3. In that order only it will try from the beginning. So it will try to assign the color C1 for vertex 3. Vertex 3 C1 is not possible because it is connected to vertex 1. So it again backtracks to the previous node, and then it will try to assign the color C2. C2 for vertex 3, C2 is also not possible because it is connected to vertex 2 which has C2 color. So it is not possible. So again this state space tree will backtrack and it will try for other color C3. C3 is not assigned to anyone, so it is possible. So this C3 color will be assigned to vertex 3. Then vertex after assigning C3, then node 3 is assigned. Now node 4 is there. So we have to assign the color to node 4. It will start from C1. C1 is possible since it is not connected to vertex 1. So C1 is given. So here this graph is 3 colorable. 3 colors are used to color the graph without adjacent vertices having same color. Now, so this is the method for exact method or exact algorithm which can be used for graph coloring problem, but it will take exponential time. So here we have given an approximate algorithm for the graph coloring problem. So planar graph coloring problem is an NP-hard optimization problem for which polynomial time absolute approximation algorithms are there. We can have approximation algorithm which takes only polynomial time. The problem is planar graph coloring problems is to determine the minimum number of colors needed to color a planar graph, GBE. It is known that every planar graph is 4 colorable. So every planar graph, there is a property that it is 4 colorable, which means maximum it will take only 4 colors. So we need to check whether it will take 0, 1, 2, 3. We'll take these options. One can easily determine whether a graph is 0, 1 or 2 colorable. It is 0 colorable if and only if no vertex is there, means V is a null set, it means no vertex. So it will take only 0 colors. If there is no edges, means only one node is there, so it is 1 colorable. And if it is 2 colorable, if it is bipartite. Bipartite is a property of the graph. So if 2 colorable. So 0 means there are no vertices in the graph. 1 means there are no edges in the graph. 2 means if the graph is bipartite. So we can check whether a graph is bipartite in time. We go of B plus E. It's the polynomial time complexity. So we can write the algorithm as approximate algorithm as here, like this: algorithm approximate color V comma E. This algorithm determines an approximation to the minimum number of colors. So if V is a null set, then it returns 0. Edge is a null set. No edges means it will return 1 and 1, which means it is 1 colorable. If G is bipartite, it is returned 2. Else return 4. All the other cases it will return 4. So only condition is whether it is 3 colorable or not. That is, you cannot tell whether it is 3 colorable or not. If it is will 0, 1 or 0, 1, 2 or 4 it will return. If it is 3 also, it will return only 4. The approximate solution only will return. So it is the approximate color algorithm for graph coloring. Approximate algorithm for the graph coloring. Similar to this, edge coloring is also possible. That is, edge coloring of a graph is a proper coloring of the edges. Instead of vertices, it is a proper coloring of the edges, meaning as an assignment of colors to edges so that no vertex is incident to two edges of the same color. Similarly, K edge coloring. Edge coloring with K colors is called K edge coloring. Total coloring means